says more mass, more force. Newton's second law is actually force equals mass times acceleration. So we kind of did that whenever we were pushing in the parking lot, whenever we pushed those waters. Would y'all agree? You kind of learned that whenever we did that. So then we proceeded to do motion maps. And what were motion maps? Yes, Devin.
You're showing like how many seconds it took for it to travel.
Shows how much time it takes something to travel, or shows where something is at a certain amount of time. So that's a scientific model that we use to show where something is. If I pretend to be the chicken again, you guys can tell me where I am at any given time as I'm moving around. So, to combine Newton's first law and Newton's second law, and really we're starting to get into Newton's third law, but I'm going to tell you guys about Newton's third law a lot more in the next 2 days. We are going to look at something called free body diagrams. And I promise this is the last type of model that you have to know for Newton's laws. But this diagram shows us the types of forces that are being acted on in Newton's laws. So, on your free body diagram entry, your paper that I just gave you, your little article, it tells you the definition of a free body diagram. But I kind of summed it up in something that I think makes more sense to us. It's a model of all the forces acting on an object. So I think that that's a really good definition that you guys could understand, right? Does that sound too complicated? Model of forces acting on an object. So go ahead and just write that down on that entry in your comp book so that you have a really clear definition. This is like a mini notes page, but we're not really going to take that many notes. It's just going to be like something you can reference. And then if you got to the part in the article where it was talking about the 4 types of forces, in 8th grade, we are only going to talk about 4 different types of forces on these free body diagrams. So we're only going to talk about gravity, applied, normal, and friction. So if you want to write those out to the side too, you can. That would be really good for you to reference whenever you're trying to label those free body diagrams. I don't draw a picture yet. So just really quick off the top of your heads, a free body diagram is about any object at all. So if I say, let's draw a free body diagram from this basket, and I'm just going to set it right here. What forces do you guys know are acting on this basket right now? Gravity, for sure. So gravity's pulling down. Now Newton's third law says for every action there's an equal and opposite reaction. Who's ever heard that before? Kind of rang a bell, but you couldn't probably dive into it if you had to. So for every action, there's an equal and opposite reaction, which means if I put this basket here and gravity is pushing down on it, this table is pushing up on it. And I agree with that because if that wasn't true, then wouldn't this basket just continue going down into the center of the earth forever and ever? Same reason as if I take this. I had a tennis ball. Where'd my tennis ball go? Have a golf ball. Oh, there it is, in front of my face. If I take this tennis ball and I drop it on the floor, it bounces back up to me. The floor exerts a force on this ball, just like the ball exerts a force onto the floor. So equal and opposite reactions is Newton's third law. We're going to get more into that in the next 2 days. So we know gravity. That force that's making it not float around and just kind of be doing whatever is called a normal force. So it's a normal force gravity pulling down, normal force pulling up. Now what if I move it like this? What if I say, what would you say that I've done? I've applied some force to it, right? I made it move. But did you hear that whenever I slide it? What is that called? Friction. So let's draw a model of that really quick. If I had to draw a free body diagram of that, it's always a box. It doesn't matter if we're talking about my laptop, this basket, this ball, my phone, these trays up here. It's always just a box. And I'm going to put it inside the box what we're doing just so that it makes more sense to you later. This is the green basket. And you guys told me gravity's pushing down, yes? So let's label gravity. And right now that basket's just sitting still. So I have gravity pulling down on this basket. And all a free body diagram is just showing you what forces are acting. Since the basket's not floating around or doing anything crazy, my normal force is equal to my gravity. I know this doesn't make complete sense right now, but it will in just a minute. Yes. Yes. Less mass, less force. More mass, more force. Mm-hmm. It is. That's why you weigh different on different planets. Okay. And is the basket currently sliding to the left or right?
Yes.
No. So my normal and my gravity are keeping it just sitting there. And then my applied, and it doesn't matter which side we put it on in this case because it's not moving. But I'm going to show you a scenario where it would be moving. My applied and my friction are the same right now because they're not moving. So here's an example of just a stable object that's not going anywhere. Some would say that this object's net force is 0. Who knows what net means? Yeah. Net means total. I wrote it up there. You might want to write that down somewhere. Net means total. Like if you've ever heard someone say, what's his net worth? Or like a famous person, you like look up how much money they're worth. You're looking up their net worth. So this is the net, the total. If something has 0 newtons, it is balanced. So this is balanced right now. Let's do one more. I'm going to erase this. Is that okay? Anybody need it? Okay, let's do one more really quick before we leave. Let's play a game of tug of war. And girls, since we won last week, I'm going to let the boys win this week because we won tug of war in my other scenarios. So, tug of war. We're about to play a classroom game of tug of war. When we play tug of war, are we floating around? So what force do we already know is acting on us? Okay, so let's go ahead and add our gravity in. And then our normal force is keeping us just standing, so we're good. And you might want to add somewhere on that paper that force is measured in newtons, because remember when I gave you that mass and that acceleration and we multiplied it outside and then you guys told me that different number in newtons? We're about to add that in here and make it a little bit more difficult. So we're standing on the ground currently. And I'm going to make up a number really quick. So this isn't real. I didn't actually calculate this. But I'm going to say that gravity is pulling us down with 2 newtons. So that means normal force is also 2 newtons because we're not floating around, we're not sinking down, doing anything crazy. I'm making up this number. The boys are going to be on this side. So they're going to be pulling from you guys' right. So they're pulling to the right. And I'm going to say the boys are really strong today. So they're pulling with 30 newtons to the right. They're pulling really hard. Girls, we're strong. We beat them last week in our tug of war. But this week, we're just missing some girls. That's probably why. So we're only pulling with 20 newtons this direction. If you had a guess, which one of these would I label my applied force? Which one? Noah?
20.
Is the applied?
No, it's 30.
30. Okay, you might want to add this too. Applied is always the higher number. If I give you a scenario that has force in it, applied is always higher.
What if they're the same number?
If they're the same, then it is 0 and it is not moving. That's not a bad question. That was a good question. Okay, so which one of these is going to be my friction? Maddie? 20. Okay, so if the boys are pulling really hard over here, 30, girls, we're like friction to them because they're having to pull against us. So, we're not done yet. Here's our friction. Now, remember how we did the net earlier and it was just 0 because it was not moving? Are we moving now?
Yes.
So we're not balanced, right? Because when it's balanced, when it's balanced, you are not moving. When you are unbalanced, you are moving. So here's how this works. 30, boys are pulling 30. Girls are pulling against them 20. 30 minus 20 is 10. And which direction are we going to end up going?
Right.
To the right. This is how you answer one of these. And this was one of the more difficult ones. So if I lost you a little bit, I promise I'll get you back tomorrow. This is a little bit more of a difficult problem. We'll break them down some more tomorrow. I do want you to have this in your comp book. And then we will go over these some more tomorrow. Put the article into your science folder. Make sure you're keeping your comp book real organized. Yes, you may. Any questions, concerns, comments so far? Good?